So welcome back to the fourth lecture in week 10, and we're going to continue looking at non-parametric filters, right? So if you remember, we started at looking at these filters as a way of doing recursive state estimation, right? So what we are going to look at in this lecture is a very special case, right, where I really want to know what my state is, what my current state is, right? And I'm going to keep on making repeated measurements, right? I'm going to continue to refine my estimate of where I am, right? Such problem settings, right, are called problems with static state, right? So I'm going to assume that I'm either going to, right, I'm not changing my state, right? My state is fixed, and I'm going to only repeatedly make measurements until I'm sure about my state. And we're going to look at a very specific instance. It's a non-parametric filter, as you can see from the slide, because it's going back to the original base filter setup, right? Not making any assumption about what the distribution is. So I'm just going to assume that it's a problem with the static state, but I'm also assuming it's a binary state problem, right? So even though now I'm presenting to you in the context of recursive state estimation, we'll see later that this binary base filter with static state has other uses, right? And it's more important in those contexts that we'll see later on, but I'm just introducing it here for you so that it stays with all the other filters that we are studying, right? So the goal here is to look at problems that are formulated as binary state problems. Basically, I have a state variable x, right, that can either be true or false, right? So my states are either x or not x, right? X can be either true or it can be false, right? And so the robot just needs to estimate what is the value of x. Is x true or whether x is false? I mean, it could be something as simple as, okay, is there a door here or the no door here? It's our door open or not open? Or as we'll see later, is there an obstacle in the cell that I'm looking at, or is there no obstacle in the cell, right? Is it clear? So what the space in front of me, is it clear or not clear? Right, so basically that's it, right? So it's a binary state estimator, right? Door open, door closed, right? Do I have fuel or no fuel? So it's a single indicator variable which is either 0 or 1, and I'm assuming that I'm going to make multiple measurements until I am satisfied with my estimate of that, right? Now, since the state is a static state, right, so the actions don't really matter, right? So the actions don't play a role here, right? The actions don't play a role because the state is static, right? So static meaning the actions don't affect the state, right? And you can see that by the fact that we don't put any in time index on the actions, but the observations still have a time index. So my belief state at time t, so notice that it doesn't say bel xt anymore, it says bel t of x. That is because my belief still keeps changing, right? So notice that my belief state is going to be only two numbers, whether x equal to 0 or whether x equal to 1. So the probability of x equal to 0 is one number, probability of x equal to 1 is another number, right? And so on, that estimate is going to change with time. So therefore I have a time index on the belief, but the x itself is static. Therefore I removed the time index from x, right? And so the belief, instead of being the probability of x given all your observations and all your actions from the past, is basically the probability of x given your observations alone, right? Given all the observations you have made up till from time 1 to time t, what is the probability of x? In this case, what's the probability of x being true, right? And so in these problems, you should remember that. So 1 minus bel of x gives me bel of x bar, because if x is not true, x has to be false, right? So 1 minus bel of x gives me bel of x bar, and this is true for every time t, right? So that's basically the problem setup that I am currently looking at. Right? So one of the things that we do, as we will see in a bit, is the belief, right? Instead of representing it as the probability distribution directly, I represent the belief as something known as the log odds ratio, right? So in probability theory, the odds of an event x, right, is basically defined as the ratio of the probability that x happens divided by the probability that x doesn't happen, right? So this is something that's quite familiar with some people. I mean, if you look at the outcome of, say, sporting events and things like that, people say, what are the odds of that happening, right? So when the odds here actually refers to the ratio of P of x divided by P of not x, right? And in our case, we can say that it is P of x divided by 1 minus P of x. So this is the odds of x happening, right? And log odds obviously is going to be the log of P of x divided by 1 minus P of x. Is that clear? So the log odds is essentially log of P of x divided by 1 minus P of x, and we are going to denote that by the symbol L, right? So L of x equal to log of P of x divided by 1 minus P of x. Now I'm just going to give you the base filter algorithm for the log odds representation, right? Just to give you the motivation as to why we are looking at the log odds representation, and then we will actually go back and derive this, right? So remember, what does my the base filter algorithm do? It takes my current belief, which is LT minus 1 here, which is the log odds at time t minus 1, right? And my current action and my current observation, right? The action at time t and observation at time t. But I don't need my action at time t because I have a static state. Therefore, I ignore the action. I only take my observation at time t, right? And so LT obviously is going to be my belief at time t, is basically this additive expression, right? So I'm going to look at LT minus 1, which is my belief at time t minus 1, times log of this expression, right, which is the probability of x given zt divided by 1 minus probability of x given zt, okay, minus log of p of x divided by 1 minus p of x. So what is this p of x? So this p of x is essentially my prior probability of whether x is true or not, right? I mean, so p of x is a probability that x is true when I have not seen any observation. So this is my initial belief as to whether x is true or not, and I keep basically adding or subtracting this odds, right? My initial odds on x every time I make the update, right? So we'll see why that's the case as we go along in the next few slides, right? So I'm just going to read the expression again. So my belief at time t, which is represented as a log odds, so LT is equal to the belief at time t minus 1, which is LT minus 1, plus log of the probability that x is true given zt has happened. So zt is observation at time t, divided by 1 minus probability x is true given zt, which is basically the probability that x is not true given zt. So this is basically the log odds of p of x given zt, right, minus log of p of x divided by 1 minus p of x, where p of x is the probability that x is true before I have seen any observations. You can think of this as the log odds. This whole expression can be thought of as L naught, right, the belief at time 0. The log odds of the belief at time 0 is essentially what this expression is. So you can think of this as LT equal to LT minus 1 plus log of this expression minus L naught, right? And once I have done this computation, I just return LT. Notice it is fairly straightforward, right? It's a very simple additive expression. And the nice thing about it is, because I'm working in this additive space and with these the logs, right, I can handle more effectively numbers that are very, very, very small, right? So if I'm in a situation where the log odds of something being true or being false is very small, right, or if the probability of something being true or false is very small, using the log odds expression, right, allows me to be more stable in my updates, numerically more stable in my updates, and allows me to handle this more elegantly. So that is the reason we go in for this log odds. And later when we look at where we use these, especially in places like map estimations, right, we'll see that the probabilities do tend to be very small, and therefore using this kind of the adaptation of this binary base filter, it's very useful in such cases, right? So one thing I want you to again notice is that in the updates here, right, so in the update here, we are using probability of x given zt. Normally, our measurement model is written as probability of zt given xt, right? Normally, we will look at what is the probability of the measurement happening given x, but in this update, we are using what is the probability of x given the measurement has happened, right? So And so this is called an inverse measurement model, right? And the reason we are using the inverse measurement model here is because our state is actually very simple, right? Instead of in the normal case, our state would be could potentially be a complex vector, right? A very high dimensional state space. But in this case, we're talking about binary state, right? So x is either true or false, right? So it's a fairly simple state. But whereas the observations could potentially be very complex. So let's go back to one of our old examples, right? The observation could be an image from a camera, right? And our state could be whether the door is open or closed. It's a binary state, right? Open or closed. But the input, right, the Z could be a full-blown image from a camera, or like a small bit of a video from a camera, right? And therefore the Z could be very complex. So if I'm going to learn the forward model, right, if I'm going to represent the forward model, then I will basically will have to represent the distribution over a very complex space, right, which is the space of the observation, which is the space of all images that my camera could capture. Now that's a fairly complicated endeavor, right? So what we do here is, because the state is so simple, we try to see if we can work with this inverse measurement model, right? So we have to be, so one of the things that you will be finding out, right, as we keep going along, is that we are learning a lot of tools, right? There is nothing like that's one single tool that's the best thing to use at every point, right? And depending on the application, depending on the situation that you are actually using these tools, you have to pick whatever is the best one for you. So in this case, because the state is simple, observations are complex, I prefer to use a inverse model as opposed to the usual forward measurement model. Okay. So now, so once I have the log odds ratio, so we'll come to that in a bit. The rest of the slide, just ignore that for the time being. Just look at this. Just edit everything I said after this slide came on. Okay. So I kept saying that the log odds ratio is the belief, right? But if you want the actual belief distribution, the belief distribution is the probability of x given z1 to t, right? So I can recover the belief of x at time t by just doing this, right? So 1 minus 1 by e power lt of x, where lt, if you remember, is a log odds ratio at time t. So how did that come about? Just take you back to the original definition. So if you look at this definition, right? So L of x, which is our log odds, is equal to log of p of x by 1 minus px. Now, if I take the log to that side, so that becomes e power L of x, right? And then I take the 1 minus px to that side, so that becomes e power L of x minus e power L of x times px. So I bring that back here. So I'll get p of x into 1 plus e power L of x, right? Take that back that side. So I'll get e power L of x divided by 1 plus e power L of x. I'll simplify that to get this expression, right? So if you take this up, you can see that it's 1 plus e power L of x minus 1, so that will go away. So you'll get e power L of x divided by 1 plus e power L of x. So that's essentially the belief expression. Just a little bit of algebra to recover the belief from the log odds. Therefore, that's the reason I keep saying that the log odds ratio is essentially the belief, because you can easily go back and forth between between each other. And the reason we keep it as log odds is that our updates are nice and simple additive updates, right? So remember that del x is the probability of x given z1 to t, right? So del x at time t is the probability of x given z1 to t, right? So I'm going to use the base rule, just if you remember that. So I'm going to take just zt alone, right? So you can think of this as probability of x given z1 to t minus 1 comma zt, right? So I'm taking that as my p and I'm moving things around. So I'm going to rewrite this as probability of zt given x and z1 to t minus 1 times probability of x given z1 to t minus 1 divided by probability of zt given z1 to t minus 1. Okay. Now we have the Markov property, right? So the Markov property doesn't go away. So as soon as I have x, right, my zt is no longer dependent on my previous measurements, right? So I can remove this. I can go back to my usual measurement model, which is probability of zt given x. So given my Markov assumption, I can go back to my old measurement model, which is probability of zt given x, and the rest of it carries over, right? Now let me try and simplify the measurement model also, right? I can apply the Bayes rule again to the measurement model, which is probability of zt given x, and that gives me my inverse model, which is probability of x given zt, times probability of zt, which is the kind of the unconditioned probability of making that measurement zt, divided by probability of x, which is my prior probability before I have made any measurements, right? You remember we already saw that in our Bayes filter algorithm. So this is where it gets introduced here, right? Now there are a few things which I don't want to compute, right? Remember, I don't want anything where zt is the variable over which I am defining the distribution, because z is a very complex space. I would like to get rid of any dependence on, or rather any place where I have to compute a probability over zt. That's the reason we wanted to use the inverse model, right? So I'm happy with this, but I don't like this, right? Nor do I like this, right? So probability of zt given z1 to t minus 1 is even more complex to determine than probability of zt, right? So I want to get rid of these somehow. So let me plug this back into the expression and see what we can do, right? So now substituting my Bayes expansion of probability of z given x, right? I get this, right? Probability of x given z1 to t, which is my belief of x, belief of x at time t, is equal to probability of x given zt, right? So probability of x given zt into probability of zt divided by probability of x into, right? So this part is done, into probability of x given z1 to t minus 1 divided by probability of zt given z1 to t minus 1. So those parts come in here, right? So I have probability of x given zt times probability of zt divided by probability of x, right? Here again the rest are remaining terms from the expansion earlier, right? Probability of x given z1 to t minus 1 divided by probability of zt given z1 to t minus 1, right? This is for the probability that x is true. I can write something similarly for the probability that x is false, and I would get these quantities, right? The probability of not x given zt times probability of zt, probability of not x given z1 to t minus 1, the whole divided by probability of not x and probability of zt given z1 to t minus 1. So here is where our thing comes in, right? So I'm going to take the odds, so which is probability of x divided by probability of not x, right, given z1 to t, right? So this is basically the odds of our belief representation, right? Probability of x, this is probability of x is true under the belief at time t, this is probability of x being false under the belief time t. So I take that and that's my odds. Please edit that. So now given that's the odds, I start dividing this, right? What is the nice thing when I start dividing? All these zt terms which are common to both x and not x will go away, right? So this zt goes away and this term also goes away. So what I'm left with is probability of probability of x given zt divided by probability of not x given zt, probability of x given z1 to t minus 1 divided by probability of not x given z1 to t minus 1, and this will go up and that will stay down. So I'll get probability of not x divided by probability of x. Right? And we all know that probability of not x can be written as 1 minus this. So I basically get this expression, right? So all the not x parts get simplified as 1 minus x. Now what do? I take logs on both sides, right? So this is my log odds for the belief at time t. So that's LT of x equal to log of px given zt divided by 1 minus px given zt. This is essentially the second term that we had in the Bayes filter expression. That's the log odds for the inverse measurement model for the current measurement zt, and then I get log of p of x given z1 to t minus 1 divided by 1 minus p of x given z1 to t minus 1. And what is that? That is LT minus 1 of x. That's my previous belief, right? So that's my previous belief, and then I have this term which is log of 1 minus px divided by px, and I can flip it around. I take minus log px divided by 1 minus px, which is my L naught of x as we saw earlier. So that's essentially my whole expression. So LT of x equal to LT minus 1 x plus the log odds of the inverse measurement model minus L naught, which is the log odds of the initial belief before I make any measurements. So that gives us the expression for the the binary Bayes filter update. So we'll go back here, and so that's the binary Bayes filter, and it might seem a little silly here because we are looking at a single state variable, but later on, one of the applications that we look at for this algorithm is where there are many such binary variables that we are trying to estimate in the world at the same time, and having a more convenient additive updates, right, are very useful. Okay, and that's it for this week.